Notes out? I see about 50% of people's notes out. Let's fix that. Make it 100. Yesterday we were talking about, Yesterday we were talking about patterns of numbers. How do you recognize patterns? Some of them you add repeatedly, some of them you multiply repeatedly, some of them you follow the list of perfect squares, etc. I want to show you a couple of technical names that they use for these things. Sequence. There are two different words you'll need to learn this section in addition to a few other things. Sequence versus series. Those are two different things. Question?
Isn't today the 12th and it's Tuesday?
Yikes. It's the 11th, but it's Tuesday.
Yesterday.
It's the what?
Yesterday was the.
Oh, you're right. Hold on. The button that lets me set the AM and PM on my watch is broken. So it's like, it thinks it's 9:51 p.m. yesterday. Welcome to my life. But yeah, it's the 12th. I was telling that wrong to everybody wrongly. Never mind. But yeah, it is. I needed to watch. Sequence is a list of numbers separated by commas.
Oh.
Go ahead and write that down. A sequence is just a list of numbers that are separated by commas. You don't have to do anything with them, you just list them. A series is a list of numbers added together. We were playing with sequences yesterday. We were trying to predict like the 10th number in a sequence or the 100th number in a sequence. Series are a little different. A quick example. 1, 2, 3, 4, 5 is a sequence. So how do you tell the difference between that and a series? This way. They're using the same numbers, but they have different results. The first one, you just list them and you're done. The second one, you have to add them up. You'll actually get an answer for a series. You will not get an answer for a sequence. You just list them. Make sense? So again, yesterday we were playing with sequences, and there are different types of sequence. The second half of the chapter, we're going to play with series. That can get very tricky, but once you learn the tricks, no pun intended, okay, pun slightly intended, then it's actually a lot easier. For example, I want to give you just a teaser for the second half of this chapter. This is a true story, by the way. About 250 years ago-ish, there was a young boy, about 8 years old, named Carl Gauss.
Why did they name it that? That is me. Oh yeah.
He was from Germany, so like they think our names are weird.
Well, their names.
Carl Friedrich Gauss,
Yes.
age 8. Yeah, go ahead and write that down. He was a famous mathematician. He became a famous mathematician, not at age 8. But when he was 8 years old, his teacher was sick, so he had a substitute teacher come in. And that, in those days, the one teacher taught everything. Like the history, math, everything. And the math level, they usually didn't go very high. In that particular area, it was unusual for people to go past 8th grade. Then they would just go and get a job.
That's nice.
Like they would apprentice themselves to a blacksmith or to, so woodworker or whoever, and they would learn a trade. Carl Friedrich Gauss, 8 years old, his substitute teacher came in, and his substitute teacher was kind of lazy. And he wanted to have a chance to just kick back and relax and give the students some busy work. So here's what he did. Now you have to understand, back in that time, what I need a prop. Let's just say,
A knife?
no. Has everybody heard the word slate before? S-L-A-T-E?
I have.
Actually, in 8th grade earth science, you might have heard of it.
I have.
Slate is actually you studied metamorphic rocks. Maybe you know what slate comes from?
Metamorphic.
When you put a
rock.
different type of rock under heat and pressure. Anybody know what rock it is?
No, I forgot.
Shale. Very good. Shale is a very oily rock, and when you compress it and heat it, it becomes slate. Slate is what they used to use and still use sometimes for chalkboards. So it's very hard, and it's usually black, so it shows up very easily if you use white or light colored chalk. So all the kids had a small slate, like surrounded by with a wooden frame. It looked like a picture, but with black on it, and they had a lump of chalk and a rag, like a literal rag and a lump of chalk, and that's what they used to write the things on. It's not very big. It's like maybe a foot tall and maybe like 8 inches wide. So they would write a little bit. They didn't have paper, not that they didn't exist, but it was expensive. So they would write as much as they could, and then erase it all, and then quick write down where they had before. So if they have a huge math problem, they'd have to erase this like 20 times by the time they get to the answer. It was tedious. All the kids had their slates, and the substitute teacher says, "Mein Kinder," the kids or whatever, like, "I want you to add up the numbers from 1 to 100. And then he sits down. And he figured it's gonna take them, like, can you imagine? It's like 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way up to 100. So here's what they'd have to do. 1 plus 2 plus 3 plus 4 plus 5, and they'd do the quick, and that's like 15. And then they have to erase everything else, start at 15, then add 6, then add 7, then add 8, and the bigger the numbers get, the slower and slower it goes. So I figured this will take the kids a half hour. He can just sort of sit and daydream for a while. He walks back to his desk leisurely, and as he's about to turn around, he hears a click on his desk. Carl Gauss had dropped his slate on the teacher's desk with the correct answer before he even sat down. He went on to become one of the most famous mathematicians in the world, but the trick he used, I can show you today. It was super sneaky, it was super clever, but it's not that hard. It took a brilliant mind to think of it. Watch this. 1 plus 2 plus 3 plus 4 plus blah 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 plus 97, 98, 99, 100. Again, most people just start adding from the left-hand side. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, and it gets harder and harder and slower and slower. By the time you get to like 64, the number is really big. And then you have to add 65 and 66, and you're carrying and heaven knows what. Watch what he did. If you add like this, it gets worse and worse, but watch this. Add the first and last numbers, what do you get?
I dream it in one. This man has eyes in him.
What's 2 plus 99?
101. 101.
What's 3 plus 98?
And then you add? Oh.
Every pair, beginning and end, adds up to 101 every single time. Question, with 100 numbers, how many pairs?
50.
50.
You can.
That does it.
I kid.
Watch this. Now this is easy. It's 0, 0, 0. This 5 times 1 is 5. 5 times 0 is 0. 5 times 1 is 5. 5,050 is the answer. Isn't that amazing? 8 years old. That guy's a hero.
That's me.
So, most of math, my old high school math teacher used to say this, most of math is discovering sneaky tricks to make your life easier. hundreds of years went by where people just slogged through long problems, and then somebody comes up with a short way to do it, and then they're hailed as a math hero, and then they're mentioned in math books. This is one of them. Carl Gauss, he did astonishing things with math. I'd look him up on Wikipedia or something like that. I'm not the biggest fan of Wikipedia, but they do have a nice article on him. They claim that this story might or might not be true. I firmly believe the story is true. There are at least a few people from back when that said, yeah, that kind of happens. And I like the story anyway, so darn it, it's true. I mean, if I go to heaven and Carl Gauss says, you know, by the way, that story was not true. All right, fine, it's not true. But it just seems there's too much detail in the story for it to be false. So, for what that's worth.
I hate it.
That's called a series. It's a series of numbers from 1 to 100. We're going to talk in the second half of the chapter how to do series, and there are tricks to that. Carl Gauss discovered a lot of them, and then mathematicians who came after him discovered a bunch of other tricks. For now, I want to talk about sequences. There are 3 basic types of sequence. There are actually more than this, but those are the more advanced ones. First, the way people normally pronounce this word is arithmetic. That's a noun. They put the accent on the I, arithmetic. That's when you use it as a noun. Put an accent over the E. Arithmetic. That's an adjective. Arithmetic means it's describing something. If a sequence is arithmetic, that means you add the same number repeatedly. We saw a few of these yesterday, where you kept adding 4 over and over and over and over to get the next number. That's called an arithmetic sequence. Anytime you add the same number again and again and again and again, you'll get an arithmetic sequence. The second one, it's kind of weird to hear this. Geometric. Geometric. That comes from the word geometry, which talks about shapes. Geometric sequences have a lot to do with geometric shapes. They show up a lot. But this refers in our class to if you multiply, oops, I can spell, the same number repeatedly. So if you keep doing times 2, times 2, times 2, times 2, times 2, that's a geometric sequence. And then the third is none of the above.
I'll take it, sure, that's right.
All the other random ones. What the book is going to do as one of your first homework problems, it's going to give you a list of like 15 sequences and say, categorize these as arithmetic, geometric, or neither.
Yeah, they did.
Okay. So now you know the trick. Some of them are a little weird because if you're adding the number 13 over and over and over again, it's not quite as easy to see. But you should be able to with a little bit of careful looking. Geometric is when you multiply repeatedly, and sometimes it's just none of the above. You remember the one we did yesterday?
Which one?
1, 4, 9, 16,
Yeah.
25. Remember that one?
Yeah.
You remember what the trick was?
Square.
The squares. That's none of the above. You're not adding the same number over and over and over, and you're not multiplying the same number over and over and over. You're just doing something else. Some of them can be clever, some of them can be just random, but they're none of the above. Make sense? So there are a lot of them that are none of the above, but they still have an interesting pattern. Some of them just have weirdo patterns they have to. I'll show you a few of those later. There was actually a brain teaser I had. My mom got me a book of brain teasers when I was like in middle school. And I didn't know how to do half of them, but one of them,
I just looked at
Can you give me the next three? And then explain where it comes from? Yeah.
Actually, no.
Okay.
Thanks for telling us.
Anyone take a guess?
You are welcome.
What? Oh, okay, so you.
What do you think the next number is?
3, 1, 1.
Not one.
No, it's
4.
Yes.
1,
1.
1,
5.
1,
1.
6.
6, 1, 7, 1, 8, 1, 9, 1, 10, 1, 11, 1.
Oh, you got 1, 1, 1, 2, 1, 3, 1.
Now, if you keep going further, what if you
Well,
went
I don't
to
understand.
11,
Why does
1,
Because it goes like around, and then it
12.
goes back to 12.
1? What's the next one?
13. 1.
It's 1.
What? Oh, you get up to 12 now. Wait, can
And you go down.
It's not as easy to detect today. If you went over to your grandparents' house, you might have an easier time figuring out where this came from.
What?
Can you?
These are the number of chimes that the grandfather clock makes.
Oh.
This is 12 o'clock, 12:30. They just give one bong. 1 o'clock, 1:30. At every half hour, it only gives one bong. And then on the hour, it gives the number of bongs that the hour is.
My bong has a big bong.
I just had no idea. No.
My grandfather clock, not my mom.
Let's not go.
Okay, we're
Your
done.
directions.
Okay, Mr. Coughlin, you may continue.
Thank you.
Brandon, just be quiet.
Moving right along. All right, people listening at home, never mind. Now,
I'm sorry.
for an arithmetic sequence,
Stop.
when they're talking about the same number, okay, no. When you add the same number and over and over and over, they have a special name for the number you use. That same number that you actually add over and over again is called the common difference. I'll explain in a second. For example, if you have like 2, 5, 8, 11, blah, blah, blah. By the way, the common difference, they have a short letter for it. They use the letter D for difference, common difference. In this particular case, can we tell me what D equals? Just look at the pattern. 3. D is 3. That basically is the world saying D means it's a common difference, you're adding it. And in this case, they're adding 3. Does that make sense? Why do they call it a common difference? Okay, math people, what is a difference in math? The answer to a what? Go, Jeff. Subtraction problem. In other words, how do you find out what they're counting by? Like how do you know how much they're jumping up by? What are you doing in your head? Subtracting. 5 minus 2 is 3. 8 minus 5 is 3. 11 minus 8. You have to do a subtraction to find how much you're jumping by. That's why it's called the common difference. Okay? Now, what do you call it if you're multiplying the same number repeatedly?
The geometry.
So for example, if you have 2, 6, 18, 54, blah, 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 blah. What are they multiplying by over?
3.
3.
3.
They call this a common ratio. I wanted them to call it a common quotient. They invented this hundreds of years ago. I wasn't around.
Wait. Oh.
So they used the letter R. They just didn't like the letter Q for some reason. I would have liked Q, but they didn't ask me. A ratio, by the way, is a fraction. It is a quotient. How do you find out what they're multiplying by? Well, how do you do that? Like if you look at the string, how do you find out what they're multiplying by? What do you do in your head? Like if like 2 to 6, what do you divide? 6 divided by 2. In this case, R is equal to 3. Common ratio. Right. And every single ratio works. 6 over 2 works, that's 3. 18 over 6 works, that's 3. 54 over 18 works, that's 3. That's how they get it. You can pick any two numbers next to each other and divide, and it'll give you the common R, the ratio. Does that make sense? Most of the homework is having you discover the value of D and the value of R.
Dang.
And finding out if it's arithmetic, geometric, or neither at all. Make sense? I have one more example, and then I think I can let you work. Any questions on this so far? I'm going to erase Carl Gauss's example.
Yeah.
By the way, look at Carl Gauss's example. Do you see the 1 plus 2 plus 3, blah, blah, blah? It's a series that they're adding, but is that an arithmetic series or a geometric series or neither? Yeah, go. It's arithmetic. Why?
Oh, I know.
Go.
Because
They're adding 1 repeatedly. So what would you say? What letter and what value?
R equals 1.
Close.
D equals 1.
D equals 1.
Go.
D equals 1 is the code for all mathematicians when they're talking about sequences to say it's arithmetic and you're adding 1.
What the heck?
If I had put R equals 1, that would mean you're multiplying by 1 repeatedly. D equals 1 means you're adding repeatedly. R equals 1 means you're multiplying by 1, which would be really boring. But you could theoretically do that. Does that make sense? Later on, we'll show you some, I'm just going to give you a tiny teaser. Quick question off the top of your head. If you add up an infinite number of numbers, what do you get as an answer? Good. Infinity is very possible. Is that guaranteed?
No.
Give me a counterexample.
It could be.
What?
I actually don't know.
Dot, dot, dot. Yes.
I don't know.
Go. 0 plus 0 plus 0 plus 0 plus 0 will not go to infinity. It'll be 0. Can anybody give me a one that has no zeros in it, but doesn't go to infinity?
Negatives.
Negatives, well, they'll sort of go to negative infinity, which is true. By the way, that's a clever idea.
Thank you.
Can anybody give me a string of numbers where if you add them all up, you will not go to infinity? Go. 0.9 repeating. Oh, that's interesting. But now you have to add up a bunch of numbers, though. That's one number. I'm going to go back to that, by the way, because that's a fascinating example. Let me show you. 1 plus negative 1 plus 1 plus negative 1 plus 1 plus negative 1 plus 1 plus
I'm so
negative
good
1.
at this.
Now, what's the answer?
Which is not zero.
Harder than you think.
Actually, no, it depends.
If there's an even number of numbers, you're right. What if there's an odd number of numbers?
It's negative.
It's either 1 or negative 1, depending on what you started with. In other words, nobody knows. Because if you go to infinity,
Jack
is
knows.
infinity even or odd? In other words, it doesn't have an answer. But I'm going to show you one teaser for near the end of the chapter. Is it possible to add up an infinite number of numbers? You know, the two tricks we found to spoil it were use negatives or use 0. Remember that? If you add up a bunch of zeros, you avoid infinity. If you add up a bunch of positive, negatives, they cancel and avoid infinity. Do you think I can add up a string, an infinite string of positive numbers and not get to infinity? What do you think? What would common sense say?
No.
Common sense says no. If you have a bunch of positive numbers, they're going to get bigger, and you're going to go to infinity.
I'm gonna cry.
And you can actually tell me what the answer is if you draw a picture. One, now this is like ancient, this is like back before kindergarten level. Here's one. One circle.
Draw a circle.
Here's a half circle.
Half it in. Draw a circle.
Quarter circle.
Fourth it in. Eighth it in.
Eighth of a circle. 16th of a circle.
It's the
32nd of a circle. That's when it keeps getting half of the leftover stuff. 64th would be a half. What if this goes forever?
You're never gonna go. Need a bigger circle.
Now, in other words, every time you get the next number, you're never going to fill it. Does that make sense? But if you go to infinity, you will fill it. Now, you just can't get to infinity. That's the problem. Because here, go that way and run to infinity. I'll wait. That's mean. I mean, you'll never see this friend again.
I can go to
So-
China.
It's like that, here.
Zimbabwe.
It's like here's the stick. Here, Fido. Here, take the stick. Go to infinity. You'll never see Fido again. So, in other words, you
Oh,
can't
you
go
should
there.
do it with the hippo.
Now-
He really cares about that. Wow. Excuse me.
Wow. Okay, now, can anybody tell me the answer? There's actually a number answer to this. If this goes to infinity, just pretend you can go to infinity and pretend you can fill it up. How much total do you have? 2. That's exactly right. Isn't that bizarre? That's actually kind of a college level problem, but we'll actually touch on that at the end of this chapter. We're not going to go into the brain busting ones they have at college, which by the way are totally fun once you get there. But it is possible to add up a bunch of positive numbers and get a non-infinite answer. As long as you have the numbers shrink fast enough. Yeah.
Okay, so.
Quick question.
Okay, so 0 times 1, it's not 1, so it can't be 1, right? Yeah.
0 times 1 is 0.
Okay, what about 0 times 2 is 0, right? So 0 times 0, 0 times. So it can't be 0 because like it's 0 times.
Well, anything 0 times is 0. Now,
So
oh.
it theoretically couldn't be 0 because it's 0 times.
There's 2 parts to that.
No, 0 times 1 is 0.
Hold on, I'm only going to take 30 seconds on this because
So-
this actually goes into the last. We actually touch on this at the end of the chapter of this chapter, believe it or not. But,
Brendan, I have homework to work.
but, does anybody remember what 2 to the power of 0 is?
0.
It's not 0.
1.
It's 1. Do you remember how? Why it does that?
Because that's just what it wants to do.
That's almost never the reason. What's 2 to the third power?
6, 8,
8. Good. 2 times 2 times 6. What's 2 squared?
4,
4. 2 to the first?
2.
2. 2 to the 0. Look at what the pattern's doing. They're dividing by 2. Do it again. What's 2 to the negative 1? 1 half. Excellent. What's 2 to the negative 2?
Positive, negative,
1
negative,
fourth.
1/4.
Which, by the way, is a geometric sequence. You're not supposed to know that yet. But that's where the 2 to the 0 power comes from. There's a common sense way to raise powers, and then there's a mathematical way to raise powers. Common sense powers is like 2 to the third power is 2 times itself 3 times. That's the common sense way to do it. 2 to the power of 3 is actually a little more involved when you do the math thing. Partially because, what about this? What in the world does that mean?
It means it would be 8.9, no, it would be like 9 point something or something. Or 8
I have no idea what it is, but
Or something or something.
it is bigger than 8.
Maybe something.
The calculator can do that.
Oh, okay.
You will get an answer.
I got my
It's going to be some
calculator.
horrible decimal.
Okay, okay, okay.
And
here you
it's
go. Here you go.
kind of like, it's like 9 point something, I think, my guess.
How do we get this?
I don't know.
It's like,
Brendan's not used to that.
Oh, it's a 0.9 repeating.
8958684. I figured that out all by myself.
Congratulations.
Brendan, you don't have that.
The short, I'll tease more on that later. The 0.9 repeating is,
Calculators.
it's actually a geometric sequence, a series actually. It's this.
So bad.
It's 0.9 plus 0.09 plus 0.009 plus 0.0009. Forever. This is 9 over 10 plus 9 over 100 plus 9 over 1,000 plus blah 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 blah. And what you do is you multiply every step. You're multiplying by 1/10, which is a geometric sequence.
Wait, but what is this?
So r is equal to 1/10. Now it's weird to have an r that's a fraction, but it does happen. So that's just a little teaser of what's going on there. That means this answer is, we could figure out what 0.9 repeating is at the end of this chapter when we do what's called a geometric series, when you add up a bunch of geometric terms. So we will cover that in about a week and a half.
Okay, cool.
We'll see.
Can we
So keep that in mind.
start on
That is all I have for you. So, oh, by the way, take out your homework guide sheets. I have to modify a little bit.
Zero times zero.
Problems 1 and I'm gonna make a trade on the problems. I think it says 1, 2, and then 4 through 9.
But I already.
Is that what it says?
Sure.
What I'd like you to do, I'm gonna put it up here. Yes, ma'am.
I don't have it. You could have like 4 through 9.
This is number 17A. I'd like you to skip number 1 and skip number 2. However,
What? What?
I want to do 4 through 11.
What?
I'm going to put 2 through.
No.
The 10 and 11 are actually quite fast.
That's what you get for working during class.
Listen carefully. 4 through 11, due tomorrow. 10 and 11 will not take all that long. There was sort of like, is it arithmetic, geometric, neither? Find D, find R. If they exist. Yeah.
If we want to, can we do 1, 2, 4 through 9? Or do we have to?
No, sorry, that would be chaos. This will be due tomorrow, Wednesday.
Actually,
So
two
for
is
people at
fine.
home,
Let's go.
this is homework 17A. I'll put this so people on the video can see it. This is numbers 4 through 11.
Cringe.
Okay. You may break into groups quietly, keep the noise reasonable, and stay focused on math.
I am pretzels.
Yep. Yeah, 10 and 11 are in set 3. Right. They're kind of repeats of problems 4 and 5.
I want pretzels
Just
right
a little
now.
more.
I don't care. So.
Oh, yeah. Yeah, people listening at home, bye-bye. So, yeah, if you could hit that, that'd be